Okay, so in this lecture, we'll continue our discussion on eutectic transformation, mainly focused on the growth part of the eutectic nucleus, which is, you can imagine, a small, nucleus composed of these alternating alpha and beta laminar structures. So in the last lecture, I think we mainly focused on um, the nucleation processes, right? So, and we, especially compare the nucleation in the eutectic structure or eutectic transition into the nucleation in, like in a pure system where you have a spherical nucleus. And we demonstrate the distinction between these two cases. I think one very important distinction is that in here, because we have two different phases, two different solid phases formed simultaneously during the eutectic transition. So you create a lot of solid-solid interface, and the energy associated with the solid-solid interface is generally much higher than that associated with the liquid-solid interface, because you have to match the lattices, different structures, you have to stretch them and glue them together, etc. All those type of things are going to increase the energy, or leads to a much higher solid-solid interface energy. Another distinction is that the growth of these small nucleus is not isotropic. Okay, so in the like nucleation processes where you have a spherical nucleus, we know the nucleus is simply going to grow in size. And for a long time, I think we can approximately consider the nucleus going to remain to be a circle or sphere in 3 dimensions. But in here, as we demonstrate, the growth of the nucleus is basically along one direction. So the alpha and beta, these very thin layers of different solid phases, they do not grow in their thickness, right? They just grow in length. So basically, they propagate in this direction. Now, this means that if you have a particular lambda, okay, which we call the wavelength, or it's just a spatial periodicity for this repeating patterns of alpha and beta. Okay, so if you have this wavelength, which is determined when the nucleus first form, right? The form through initial fluctuations, which we do not really focus on at this stage. But after the nucleus form, once the lambda is fixed, lambda going to remain to be the same for all of the subsequent growth processes. So lambda is not changing during the growth of the eutectic nucleus. Now, this is a distinction between eutectic transformation and normal nucleation growth, right? So we have a very important length scale, which is the wavelength lambda that we analyzed in the last lecture in detail and show why this is important, right? So this is the characteristic length scale for these structures. But different from the characteristic length scale for spherical nucleus, which is simply the radius, this length scale does not change, does not evolve during the growth processes, right? So now this leads to a kind of a distinction when we analyze the critical size for this length scale, right? So in the spherical nucleus case, right, because of the radius is growing, so we can simply get the critical nucleus by setting the derivative of delta G equals 0, right, in that case. But for now, because the wavelength is not changing, so whenever you form this particular, laminate alternating structure, it's going to remain to be like this. So the condition for the critical wavelength is simply the delta G at this lambda star equals 0. We're not looking for the derivative, right? Because even you look at the derivative, you're going to have a positive energy change, but this positive energy change will not be reduced. So we will not use that point. We just use the point where you have the right lambda, so there's no difference between the energy, solid and liquid energy. When we talk about solid, we consider both the interface and the bulk-free energy reduction, which is this term, and this is the contribution of the interface. We set this whole thing to 0, and also we consider this very familiar condition, the bulk-free energy reduction is linearly proportional to the degree of supercooling delta T naught introduced in the system, right? And using these conditions, we can compute what is the critical lambda, okay, the critical length scale for the size, or not characterizing the, in certain sense, the morphology or geometry of the nucleus. Okay, so that's that, and we clearly see again you have this 1 over delta T naught dependence on lambda star. This means that if you have a much larger supercooling, you can afford a smaller lambda star, which again is easier to form by fluctuations, right? So that's nucleation. I hope this is very clear. And then we talk about the growth. Yeah, we talk about the Gibbs-Thompson effect, but I think that is pretty clear because we're going to revisit this during the growth. So let me just start from here. Okay, so I think this is where we left behind in the last lecture, right? So, and I think we also clear that, in order for these alpha and beta, so now I'm looking at a very small portion of the solidification front of the system. If you look at on the bottom, right? So this is one um, alpha plate. I'm sorry, this is one alpha plate, and this is one beta plate, one alpha layer or one beta layer. Okay, so and this is the interface between the liquid alpha and the interface between the liquid and beta, right? So now basically, as we already said before, right, far away from the solidification front, the liquid is going to have the equilibrium composition, which is eutectic composition. But near the solidification front, right, in order for the solid to really grow, so for the alpha phase, we know this is A rich, right? So it wants to repel as much as possible, as much B atom, as many B atoms as possible. So basically, what happens in here is that this particular region of liquid wants to repel the B atoms to the liquid region, which is right in front of beta phase, which wants to take B atom. And for the same processes, this liquid region in front of beta phase wants to repel A atoms in this region, which is going to be taken by the alpha phase, right? So basically you have a transport of both A and B atoms. And for our purposes, we're just focus on the B atom, but you can do the same analysis for A as well. Okay, so let's focus on the B atom. Now we know that, in order for the eutectic, this transformation or the growth of the solid phase to proceed, right, with a particular velocity v, and if we assume a steady state velocity v, right, so this means that there has to be a continuous transport of B atom in the liquid right in front of alpha phase to the liquid right in front of beta phase, right? So you have to have continuous transport of B atom. But we also know that in these systems, the transport of the solutes are basically driven by diffusion, right? So this means that based on the Fick's first law, if you want to maintain a continuous flux of B atom from the liquid in front of alpha phase to the liquid in front of beta phase, you have to have a steady state or a very stable atomic flux. And we know flux is proportional to the gradient. But for now, we just consider we have a very simple linear approximation. The gradient is approximated by the difference between the composition in these two different regions divided by the corresponding distance lambda. And I said that there's a factor of 2, which I didn't include here, which will be included later. But roughly speaking, this delta x over lambda gives you an estimate of the gradient, right? And then the flux is proportional to this gradient. Okay, so this is very reasonable of the kinetics. And then but we will simply last lecture we basically say, okay, so basically the propagation velocity v gonna be proportional to this atomic flux with a constant of proportionality, which is k1, and we can absorb the factor of 2, which we missed here, to the k1. Okay, so why here we do not use a reverse conservation equation to derive this? Because now we're dealing with two-dimensional system. So the diffusion equation in principle is two-dimensional in case, and the conservation laws are also two-dimensional, involve integrations of the complex gradient, the concentration field, which is not quite easy to deal with analytically. But so here we do not derive that, but just to present the results. Okay, so this is not only approximation. I think it's almost a rigorous result up to the first order. And so the propagation velocity is directly proportional to the difference of the concentration in this region and this region of liquid over lambda. Okay, so that's what we know. So that's I think the key finding for this. Now,
Dr. Chia,
yes.
what about the diffusion of A atoms? We don't.
So the A atoms is actually going in the same direction. In here, we set up a very simple system. If you look at this, the free energy curves are all symmetric.
But one phase is like A rich and the other is B rich, so they're moving
Yes,
in opposite.
No, the flux are moving opposite direction, but we're looking at the gross velocity, right? So now if you're looking at the B atom, so basically this, you can basically say that this tells you how, how quickly this beta phase is going to move in this particular case because it takes B atom. But the problem we set up here is because the free energy curves are all symmetric, at least in this approximation when you have fairly small delta T naught. What is the consequence of the symmetry in terms of the resulting um, atomic flux of both A and B atom? If I have this very symmetric setup, what's going to be the consequence?
They're going to be same.
They're going to be the same, exactly. That makes sense to you? So basically, the rate of flux for B atom is the same as the rate of flux for the A atom. So basically, this basically justifies why it's sufficient for us to only look at one particular species, because the other ones works basically, in the exact same way. And because the symmetry we induced, which simplify the problem, so we know that A atom diffusion occur at the same rate. So you only need to construct the one coefficient which is proportional to, delta x. We do not say delta xb or delta xa, is because they're symmetric, and this delta x is basically the same. There's only one flux and kind of one numerical gradient. Does that make sense to you? But if you're talking about a very, in reality, if we have, say, a complex alloy with a non-symmetric growth of A and B, there will be different issues. But in those cases, you have to go back to the two-dimensional solution. But in here, we're illustrating the key ideas. So this assumption, or the simplified assumption, won't change any insights we're going to obtain, and it will make our analysis much more easier. Does that make sense to you?
Yes.
Okay, that's a good question. So yes, indeed, A atom also influenced the growth, but because of the symmetry, so we analyze one type of flux, the other one will be identical. So this will allow us to write down the growth velocity or propagation velocity in this very simple form. Okay, so yeah, but that's a very good question. So that's just where we are, right? So we get this propagation velocity. Now, the next thing that we need to do is that, all the other parameters, we are okay. D is diffusivity, K1 is a proportional constant. We can get this either from experimental calibration or from computer simulations. Lambda is intrinsic to the nucleus, right? So all of these parameters we know, and the only thing that we probably need to work out is what is delta x. Okay, so, and in the last lecture, we also provide some hints on how we should work out this, right? So again, in order to get out delta x, and first we know delta x is simply the difference between this xbl in front of alpha and xbl in front of beta, right? These are the two composition of B atom in the liquid region in front of alpha phase and in front of beta phase. Okay, so they are the liquid composition, but the liquid composition is different right in front of these two different phases, because in this region, we have a lot of kinetics going on. We have a lot of atomic flux. The alpha phase takes some of the liquid and solidify that liquid, repels some additional atoms. So there are a lot of kinetics here. So right in front of these regions, the liquid composition is far from being the equilibrium XE, which is eutectic composition, which is at which the transformation starts, right? So because there's a lot of kinetics going on here, so the liquid has a distinct different composition than the far field average composition. Okay. Another thing that we also assume is that because we only look at a very local region, right, and this solidification occurs and diffusion occurs in this region sufficiently fast, because it's deals with very small length scale. So we can consider that even for a very short period of time, diffusion can actually equilibrate things in this very small region. Okay, with that assumption, and based on the free energy considerations, we can basically estimate, or at least qualitatively see what should be the combination of the liquid region in here and the liquid region in here, right? So now, if we consider the equilibrium between the liquid and alpha phases, right, we already know a procedure to get the composition of the two phases when they're in equilibrium, right? So how do we do that? We use double tangent construction and free energy curves, right? So now if we want to analyze this particular region, which is a liquid in front of alpha, so I should consider the equilibrium of alpha and the liquid. So in this case, I think I can randomly choose a free energy, which is this one. So this is suppose is my Lambda is my current wavelength for the eutectic structure. Okay, now this dashed curve basically shows the free energy curve for the alpha phase. Okay, and this very nice solid curve shows the free energy of the liquid phase. So now if I want to consider, the liquid is in equilibrium with the alpha phase associated with this particular lambda, what I should do is to simply construct the double tangent line, right? Which is the line tangent to both of these two free energy curves. And the intersection, or the tangent point on the free energy curve for the liquid, which is this one, gives you the corresponding composition. So this is my composition axis, which I didn't show here. But if you get this point and just do a reading here, you get the composition, which is XBL alpha. I hope this makes sense to everyone, right? This is clear. Now, following the same consideration, right, we can get the composition for XLB at beta, right, which is the composition of the liquid phase right in front of the beta. Uh, so following the same procedure, we first identified the free energy for the beta phase at this lambda, right? And this is the the liquid free energy curve. So you do the double tangent construction, right? And then you only focus on the liquid because I do not care what is the composition of beta phase for now. So this is gonna give you the XB liquid for beta. Does this make sense, everyone? This is how we get the two compositions, okay? And you can clearly see now that the two compositions are quite different, right? So they're different by this delta X, okay? But one important thing that we need to realize is if we change lambda, right? So here, so the composition difference, which is basically the difference between XBL alpha and XBL beta, that based on which we compute delta X. These two values are based on the double tangent construction, right? And so they dependent on the position of the free energy curve for the solid. So liquid does not change because the liquid free energy does not depend on lambda. Okay, but for different lambda, we know the effective solid free energy for both phases is going to change, right? So if lambda is small, so basically when lambda is infinity, this means that you have like a bulk alpha phase and a bulk beta phase. So there's no effect, or minimum effect of interface we can ignore in those cases. So that's going to be the lowest possible position for the bulk free energy, for the free energy of the two solid phases that you can ever achieve in the system, right? Whenever you have a lambda not equals to infinity, a finite lambda, this will always cost certain surface energy, right? So your free energy curve actually increase because you have a higher energy associated with a nucleus, eutectic nucleus with a finite lambda. So your free energy curve increase a little bit. And because the free energy curve, the position of the free energy curve change with lambda, as you can imagine, right? The position of the double tangent construction, or in particular, the composition of the equilibrium composition of the liquid phase will also change as a function of lambda, right? Because the free energy curve going to change up and down as a function of lambda, and this is going to affect the position for the double tangent construction. So the difference between the two composition can also change. So lambda, so basically this implies that delta X is a function of lambda, okay, through the analysis that we just went through. Okay, so now, there's one important case that is worth pointing out, which is when lambda equals to lambda star. Okay, so we know the physical meaning for that case is that okay, at lambda equals lambda star, my solid phase and liquid phase have this equivalently. This is not a very good drawing, but you get the idea. So all three phases in this case are in equilibrium. So lambda star means that okay, I have a supercooling delta T that's going to give me a free energy, bulk free energy reduction advantage. But because of my lambda is so small, I use all of the bulk free energy reduction to overcome the interface energy increase. So at this particular T, which we call T star, let me write down this for you. Okay, equals to TE minus delta T naught. My lambda star, just to give us a eutectic nucleus, is marginally stable, right? It's just critically stable with respect to liquid. So if you do the double tangent construction, you will see that all three curves share a single tangent line, which means the liquid, and if for this lambda star, okay, so the composition of the liquid in front of both alpha and beta phase equals to one another, which are all converged to this single point. So this means that for lambda equals to lambda star, delta x simply equals to 0. Does this make sense, everyone? Okay, but as you increase lambda, you clearly see that, okay, for lambda greater than lambda star, which my free energy curve, kind of moved down a little bit, I increase my delta x, and I keep on doing this, right? So until I reach lambda goes to infinity. So that's going to give the lowest possible solid free energy curve location. And when you do the double tangent construction, you're going to get the largest delta x. So again, we see that, okay, we know delta x is basically dependent on lambda, and we know that when lambda equals lambda star, delta x equals 0. Okay, but what is the consequence of delta x equals 0 in the kinetics? If I don't have, any, delta x, the difference between the composition, do I have any kinetics, any transfer of atoms? No, right? Because I have, if my delta x equals 0, this means that I don't have any driving force for the atomics to move around, which means that I cannot change the composition of the liquid and solid, and everything just remain to be the same. So this is basically means, okay, you have the critical nucleus, and that one will not grow, right? So for the same reason that ice and water at T equals to 0 degrees Celsius will never change, right? They're in equilibrium, they're both happy. In this case, none of the phase is more advantage than the other, so just remain to be that. Okay, first, it's the same thing here. We show that, okay, it's no kinetics. So, if I have a critical nucleus, it wouldn't grow. Okay, so now, we basically, we analyze all these processes, and we point out that your delta x depend on lambda, but exactly how? Okay, so this is where the another manifestation of Gibbs-Thompson effect, but not in forms of um, the readers, but mainly in terms of lambda. So, I will quickly go through this analysis, which is kind of straightforward. So the whole thing to realize is that we have a couple of linear approximation here. Lambda is inversely proportional to delta t. Okay, so the basic idea is that if we look at the kind of the double tangent construction. So if you look at this line and this line, can you imagine these are kind of the double tangent construction lines or similar to that? Okay, so we are looking at, this is delta T naught, which is the, let me highlight that for you. So this is the overall supercooling. Okay, so this is very much like a computational supercooling that we went through in the alloy certification cases. Okay, so and depending on where my free energy is, right, where my lambda is, I have these T curves depend on the composition as well as the lambda. Okay, I can have these T curves move up and down, right? Because basically I change lambda, I change uh, the effective supercooling I felt by the nucleus. Okay, and we know that this is linearly inversely proportional to lambda, right? So as we showed before. So when you change lambda, you know that you're changing the effective melting temperature, okay, and you're changing the degree of supercooling that nucleus fill, right? So that is basically set up. So suppose that we have lambda goes to infinity, okay? In this case, as we said many times, in this case, we have, just a bulk form. So the systems are very happy and they actually reach the theoretical melting temperature, which is TE, right? But if you have a finite size lambda, you know that you have to lower the temperature, okay? And use certain level of the supercooling to actually stabilize these interfaces. So in this case, you lower, okay, the effective melting temperature for the system, okay, by this amount. Okay, and that amount is proportional to lambda, is inversely proportional to lambda. Okay, so and this basically shows you the relation how the degree the how to say that the remaining supercooling or the supercooling used by stabilizing the interface affect the temperature and also affects delta X. The thing to realize here is that we have also derived this in the compositional supercooling case, that the delta X is kind of proportional to the degree of supercooling that you feel. Okay, so if you have the full supercooling, which is associated with lambda goes to infinity, okay, we have the largest possible composition difference, which what we call delta X naught, okay? And based on this very simple illustration, we know that if you change lambda, okay, you reduce the effective melting temperature and you also change the difference, okay? So this difference, change of difference is proportional basically to the change of the effective supercooling that you're feeling. Okay, and we know that this effective supercooling is proportional, is related to lambda through this well-known relation of 1 over lambda. Okay, so that's basically how they're connected. Okay. So I won't go through the mathematics, but the point is that we know lambda is inversely proportional to temperature, and we know that delta X is linearly proportional to the supercooling. Okay, so through these two relations is, there's a couple of lines derivation, which is similar to the ones we already show a couple of times, but you reach this conclusion. Okay, so delta X naught is the difference of composition, okay, when lambda goes to infinity. So when the lambda goes to infinity, have the largest degree of difference of the composition, okay? And you can clearly check this is a case because if you plug in lambda goes to infinity, the second term goes to 0, right? So you end up with delta X equals X naught, okay? And as lambda decreases, you have a smaller and smaller composition difference. Okay, when lambda equals to lambda star, and this factor equals to 1, this ratio equals to 1, so you have no composition at all. Okay, so this is, again, a very familiar form of manifestation of Gibbs-Thompson effect through the same analysis went through many times. Okay, so now what is the purpose of getting this? If we know the dependence of delta X in terms of lambda, okay, and we plug this back into our original expression for V, now we get some very interesting results. So again, I'm combining these two together, okay? So again, there's some constants which I change a little bit because absorb there's some proportionality constant here as well. But anyway, so the K2 and K1 basically are proportionality constant, which will be determined by the experiments. So it's not quite important what exact symbol we use, but it's some constant that need to be tuned by the experiments and tuned by probably the morphology of the solidification front as well. Okay, but that's not quite essential. Okay, the key thing that I think I want to bring to your attention is that first we have this relation between V and delta T naught, right? This is the imposed supercooling in the system. So the larger supercooling I have, the larger growth velocity in general, right? This is clear and is quite familiar now. But I want to also to look at the dependence of the velocity on the wavelength. Okay, so that this looks familiar. That's the velocity, growth velocity, the dependence of the growth velocity of the eutectic phase on the critical wavelengths on the wavelengths. That this looks familiar. This relation. Where have we seen this before?
For the nucleus case,
For
also
the
we had.
instability, right? So we have a planar interface, and suppose that we have a small bump on this interface, which is characterized by a tip radius r. Okay, we show that in those cases, the growth velocity of this bumpy interface is also depend on r with a very similar relation like this one. That ring a bell? Okay, so now you see this is where where the Gibbs-Thompson peak, why they have very similar expressions is because both of these cases are kind of associated or are governed by an interplay between a characteristic length scale and thermodynamics. Okay, so that's why they end up with very similar expressions. Okay, and you know that whenever you see this, okay, whenever you see this expression, there will be a competition between large and small wavelengths, right? Now, what do I mean by that? Okay, so in terms of the concentration gradient, right, you want the wavelengths to be small because if you have a small wavelength, and you can have a large concentration, right? If alpha and beta, the distance between these two are small, if you have the same delta X, you're going to have a large concentration gradient, you can have a large flux. Okay, this means that transport is faster and you can probably grow faster. But we know too small lambda is not good, because if lambda is too small, this delta x is going to be too small, right? Even if you have a large, you have a small distance, but your delta x is small, and this will not necessarily give you a large overall flux. So that's where the competition comes from. Okay, so you see that kinetics always favors small length scale, but thermodynamics favors large length scale. So these two are competing with one another. Does that make sense? Okay, so now if let's keep on doing this. So if this is, physically understandable, okay, so now let's move forward. Okay, so I think the next step is that because we know there is a competition, okay, set up here. So, and because of this particular mathematical form, so we know that there's going to be um, a local maximum for the growth velocity, right? And also at this stage, I think especially after homework 3, we should know very well how to do the analysis for the local maximum. Okay, so we just take a derivative of velocity with respect to lambda, and set that to 0, and we can solve for this equation. And I will skip these steps. I think the final solution is this, but I need to double check. Again, I think there might be some factor issues, but the key thing that this factor of 2 can be absorbed in here. And if we're just looking at the scaling, we know that V naught is proportional to delta T naught, but it's inversely proportional to lambda star. Okay, so this is basically the fastest, the maximum growth velocity you can achieve for the system. Okay, but this also tells us that, okay, if I have a eutectic transformation, okay, system, and I have a particular supercooling, okay, initially I may see, nucleus with different wavelengths, they all form, right? But eventually, okay, I will see that one wavelength gonna dominate the entire system, which is a wavelength selected by this particular analysis, right? So for a particular given delta T naught, you have a lambda star. Now we know that this wavelength, okay, this 2 lambda star, okay, which is the wavelength that give you the maximum growth velocity, going to dominant because it grow much faster. Okay, so going to expand into the largest region, and it's going to give you. So if you look at your tactic structure, you may see different wavelengths, but the one, the dominant structure, going to be associated with the maximum growth velocity, which is given by here. Okay, so that is another example that you can have this geometrical imprint, right? Encodes thermodynamic signature, which means that, by measuring the wavelengths, right, you have, clearly well-defined lambda between the black and white stripes, right? So if you can measure the wavelengths in this image, which I didn't give you a length bar, but I think the overall length scale for this one is probably 400 microns. So the wavelength is about 20 micron. I'll say 10 or 20 microns. But anyway, so you have that, and you can actually go back to infer a lot of useful information of the processing condition for the system. Okay, so and also this allows you to, for example, to control the processing condition. If you want to, achieve, for example, certain lambda for the structure, now you can determine what is the supercooling you want, right? And use that to actually produce a eutectic structure with this engineered microstructure, for example, with a particular lambda star or 2 lambda star. Okay, so that is basically the information here. By considering the relation between these guys, I think here lambda naught is simply lambda star. So we can actually have another two very useful relation that typically used in analysis of eutectic structure. The first one is, so if you look at the relation between these and realize that T naught is inversely proportional to lambda star, okay, again, we do not care about the coefficient, but if you just plug in T naught, is 1 over lambda star, you have lambda star square here, right? Okay, but if you take this to the left of the equation, on the right-hand side, you're going to have a constant. K2 is a constant, D is diffusivity, which is fixed once the material is fixed. Okay, so you have this scaling relation. V naught, which is maximum growth velocity, times lambda naught, which is the lambda star in our previous analysis, squared, is equals a constant. Now, for the same reason, you can plug in lambda star equals to 1 over T naught, okay? And from this relation, you have V naught over dot T naught squared equals a constant. Again, these are typical relations that people use to analyze the eutectic structure to get some useful information about kinetics and thermodynamics of the processing and vice versa. Okay, so with that, I just want to summarize about the eutectic transformation. So in here, we introduce, again, revisit, I would say, the concept and examples of eutectic transformation. We talk about the concept of nucleation, in particular, the importance of the wavelengths, the critical wavelengths here, and make a comparison, especially to the very simple spherical nucleus case. And then we introduce another manifestation of Gibbs-Thompson effect in eutectic transformation. And finally, we study the growth kinetics and show that in eutectic structure, you also have a wavelength selection processes. And this allows us to actually get some very interesting thermodynamic signature by analyzing the eutectic structure. Okay, so that's, I think, all I want to say about this system. Okay, so if we don't have any questions, I think I need to also start a new topic. Okay. So that is eutectic. Okay, so now if you look at the phase diagram, after we talk about eutectic, we're done with the solidification of alloy, right? Because again, we're looking at a very simple phase diagrams like this one, which is a typical eutectic phase diagram. Okay, so if you think about what we have discussed up to this point, we talk about this regime in detail, right? So we talk about this nucleation growth regime using the directional solidification of alloy bar. Okay, and in those cases, again, it's a one-dimensional system, allow us to write down a lot of analytical results and obtain quite useful insights in the general process. Okay, so this is like normal nucleation and growth processes. Um, and so that is this part. Okay, sorry, I should use a different color. But anyway, so you see that the first solidification scenario we analyzed is basically like this. Okay, so this is the normal nucleation growth processes. And then we focus on this branch where we talk about eutectic transformation, which is also commonly seen, transformation pathway, take you from liquid to solid. Okay, so these are the two solidification in alloy. Okay, and we already discussed both of these, distinct cases. So we're basically done for the solidification part. Okay, so now from now on, we're gonna focus on solid phase transformation. Okay, which is supposed to be the major part of this class, but we wait until the later stage of the semester to talk about it, because we need to use all of the previous stuff that we already discussed to establish understanding of thermodynamics, understanding of kinetics, and basically understand how they work together to determine the transformation pathway in different systems. We first analyze solidification, which is a little bit easier, and then we gradually add on complexity, and now we look at solid transformation. The advantage of this approach is that because we're very familiar with the liquid transformation, and when we talk about solid transformation, we can just use the liquid as our comparison and see what are the differences. Okay, so it's very easy for us now to understand different solid transformation. But anyway, now starting from today, we're going to focus on solid transformations, which also, has a lot of interesting topics. But we're going to focus on the first one, the simplest transformation, which is the nucleation growth processes in solid transformation. Okay, so now, if you look at the phase diagram, again, we focus on a path A, right? So if you start with a liquid state, you're going to get through all of these solidification processes, and you're going to get this alpha phase field in this large wide region. Okay, now, okay, if you keep on going, okay, so if you keep on going through these processes, eventually you're going to reach this point. Okay, so this is where you're going to have alpha and beta transformation. And then we analyze this when we first introduce phase diagram. So if at this low composition, if you just go through this alpha and beta solidus, what you have is you're going to see the beta phase nucleate in the alpha phase field, and they start to grow. Okay, so this is very much like a nucleation growth processes, but you're not nucleating solid in liquid. You're nucleating a different solid, which is beta phase field, in the alpha phase field. You're nucleating a solid in a solid. Okay, so this is what we're going to deal with. Okay, so as you can probably see, this process shares some similarity with the liquid solid transformation through the nucleation and growth pathway, but also they have some very unique aspect that we have to discuss in detail. Okay, so that's basically the motivation for what we're going to focus on for the next few lectures. But with this overview, let me go back to the topics that we want to cover. Okay, so again, as I said, we're going to focus on solid phase transformation in the next couple of lecture. We will first talk about nucleation in solid transformation. And again, as you can imagine, we have to go through this list. We have homogeneous nucleation, for which we will understand the driving force and energy barrier and the critical nuclear size and the nucleation rate. And then we're going to do the same thing for the heterogeneous nucleation. So if you look at this list, this is very similar to the nucleation in the pure system or nucleation in the alloy during the solidification process, right? So that's why we talk about those cases first. Okay, so now let's get to the real part of this lecture. So, from the analysis, we know that, from the phase diagram discussion, okay, we basically say that we're going to focus on this transformation pathway, right? And here are all different kinds of a schematic showing all different types of solid nucleus that you can possibly have in this particular transformation pathway. So first, you can have homogeneous nucleation. So if you look at it, what you have here is that you have very large alpha phase field. In here, alpha phase are shown like yellowish, this large color. We have green structures, right? Because we're already started with a solid phase. So in this is more like the real homogeneous nucleation. You have a different solid phase, which is the beta phase, which is shown as the red here, growing out or formed from a alpha phase field. We can call this homogeneous alpha phase field or single crystalline alpha. Okay, so this is homogeneous nucleation. Okay, but this is the typical thing that you will see in the liquid, right? But in a solid material and solid phase transformation, now because alpha phase has a microstructure. Now this microstructure means a lot of things. Means that you have the grains, you have the grain boundaries, and you have all different type of defects. Like you have dislocation lines like that, and you have layers of dislocation pile up to give you a twin boundary, and you have some other small defects, nano defects, things like that, and you may have precipitates of other things. Okay, so all these are defects in the in the alpha phase field, right? So clearly the most important defects are the green boundaries, and all these defects can potentially interact with the beta phase and influence the nucleation of the beta phase. Okay, now the general rule of thumb is that whenever we have defects, these defects apparently are more attractive for beta phase for the nucleation. Okay, now, for example, you see that it's probably not it's a schematic, but as we show here, you have many nucleus, right? But you only have one occasion of homogeneous nucleation, which is right here, and all the other nucleations are associated with different defects. For example, you have nucleation near the dislocations or the twin boundaries. You have nucleation affected by these nano defects. You have nucleation affected by the precipitates, right? But besides all of these, I think the next most commonly seen nucleation mechanism is that you have nucleus formed on the green boundary. Okay, so like this is a triple point, this is a binary, there's another triple point, triple point here, triple point here. Okay, so this is a schematic, but from this analysis, there are two take-home points. Number one, again, homogeneous nucleation is very rare in the solid transformation. Number two, nucleation or heterogeneous nucleation, I'll say, is significantly affected by the existing defects in the solid structure of the alpha phase. Number three, green boundary nucleation is very, very, very commonly seen, okay, in these systems. Okay, so I hope this makes sense, right? So again, I'm assuming that we're looking at a real image, but this is schematic. However, the insights we obtained here is, I think, actually also it's true, okay, to the real system. So now, based on this analysis, we'll just focus our subsequent discussion on two occasions. The first one is homogeneous nucleation. Okay, again, this is rare, but we can still have this as a very clean reference case for understanding more complicated nucleation scenario. And the next one we're going to deal with is the green boundary nucleation. Okay, we'll see why we deal with green boundary nucleation. Well, because it's mathematically easier to deal with, and secondly, because it have insights, right? Will allow us to understand what are the contribution of the defects to the nucleus, and this insights can carry to other defects. Okay, does this make sense to everyone? Okay, so let's start our discussion. First, we look at the homogeneous nucleation. So I just basically steal the same. I will say the same diagram I used for homogeneous solidification. Okay, nucleation for solidification. But now the difference is that in here, the blue illustrates the alpha phase. Okay, and it's a single crystal. So I have a alpha phase single crystal, and now I create a beta nucleus, which is a solid. Okay, and this is also solid, right? It's a solid nucleus with interface. Okay, so this is our setup. Now, it's very clear to us that in this case, I have a spherical nucleus, I have the surface area A, and I have the volume V, right? Though these two things, and we know that, okay, the reason why you have a nucleus is because beta phase have a lower free energy compared to alpha phase at this temperature. So when transforming a small alpha into beta, you have a bulk free energy reduction, and this is going to contribute to a negative of the change of the free energy. And we also know that because you have the surface, which is going to contribute to the surface energy, this is going to give you a barrier for the nucleation. And this is all we need for solidification. Okay, but for the solid transformation, do we need some extra terms, or do we have to consider extra contributions to the change of energy? Okay, so if I think one way to think about this, that if you consider these are Latin system, so alpha phase has a FCC structure, and beta phase has a BCC structure or BCT structure.
The change in the crystal structure will need some energy also.
Exactly, the change of the crystal structure, right? Well, why is that? Well, because the two solid have different crystal structure. So this means that if you have the same amount of this, 1 mole, for example, or a very small fraction of a mole of nucleus form, this means that you convert some part of alpha into beta phase. The mass is the same, but the volume will be different in general. Does this make sense to everyone? Because they have different crystal structure, so this is going to generate different volume, right? Does this make sense? Okay, now you may ask, okay, why we don't have to consider this volume change in the solidification processes? Because in general, we know when water freezes into ice, the volume change. Well, the reason why is that water is a fluid, right? If you have a smaller, larger solid insert into the water, it won't actually play any role because the total volume of the water just expand a little bit, occupy a little bit more of the container because they're the liquid, right? So but this is different than the solid, right? Because the solid cannot flow. They cannot easily adapt their shape and total volume in response to the change or volume in a small region. What happens is that basically you can imagine that BCT is a less dense packed structure, right? So if you have this amount of solid, right, alpha transform into beta, what you have is actually a slightly larger nucleus. Suppose it's still spherical, but because BCT has a larger volume per unit mole or per mass, so when you convert this amount of alpha into beta, you actually have a slightly larger, smaller, a spherical nucleus, right? But now I have to fit this slightly larger nucleus into the same volume in the system. Now, in order to do that, what I have to do? I have to squeeze, right? I have to really, I'm just imagine what's going to happen, right? So, and we're going to see the consequence of this. So basically what I have to do is I have to squeeze this nucleus, right? And to the same size before, and then insert that nucleus in there. So we have this scenario. Does that make sense to everyone?
Won't
Okay.
that create vacancies in alpha phase? Like,
I'm sorry. Well, I didn't get the question.
what about the alpha remaining, uh, the part
Yeah.
that we squeezed?
No, so
There will be changes in the remaining alpha.
it will change. So basically, I'm thinking that suppose that you take this hole, just you dig a hole in the alpha, right, and take that alpha, convert that to beta, and you know that that beta going to have a larger volume, right? And in order for the beta to fit in the hole, I have to squeeze the beta and try to fit in the hole. But after that, beta tries to expand, right? It's not going to be easy because initially you add forces to constrain beta into that volume. But then if you put into alpha phase into this hole, the force are removed. So the constraint can only coming from the nearby beta or the nearby alpha phase. So the beta phase is gonna then try to expand and push onto the alpha phase. Okay, and this basically means that in the local region of this alpha beta interface, the alpha phase is compressed, right? And the beta phase is also compressed because I have to squeeze. Does that make sense to everyone?
Professor, I have a question.
Sure.
But this is assuming that the beta phase is has a higher volume, right? Requires a higher volume. What if it's the other way around? What if the beta phase requires lesser volume than the hole that we've created?
So when the beta phase has a less volume, it has to. So the beta phase is gonna pull everything in. The reason why is because we assume we have a perfect coherent interface. So on the interface, atoms still have pretty good adhesion among one another. So in this case, basically after the transform, the beta phase wants to shrink, but alpha phase constrains the shrinkage. So the beta phase is gonna pull everything. Okay, this also causes basically you have a tension field near the beta alpha interface. But the whole point here is that because of the solid transformation, you have a mismatch of the volume. Either the volume increase or decrease, you're gonna generate a volume strain, right? Because when you either compress or the pull the other phase, you actually generate a strain field in the whole material, and the strain field is long range, so it's a volume thing. It's not just a surface. Okay, this is a point I'm trying to make here. Okay, and we don't have this in the liquid, right, for obvious reasons, but we have this for the solid. Okay, so now based on this general consideration is that, besides these two energetic terms, we have to also consider another term, another contribution of energy. Okay, and this energy is from the strain energy, which I use S to denote, or stress energy, if you want to call that, but typically we use strain. Okay, strain energy, due to the mismatch of the volume when you form the solid nucleus, and because you're inserting this new solid into another solid alpha field, right? So the strain cannot be relaxed naturally. So this will manifest it as a bulk strain energy, and it actually serve as another barrier for the nucleus because you increase the energy of the system in this particular case, right? So they have plus of this, and it's proportional to the volume because strain energy is kind of a volume energy density. So that is one distinction between the solid nucleus and solid liquid nucleus. So yeah, so basically, in order to consider the solid phase transformation, we have to consider the strain energy due to the volume change, and this give you additional term here. Okay, so now if we, basically we write down the geometry for the nucleus. If we assume that we have a spherical nucleus, right? We can write down the volume in this like this, and the surface area like that, right? But and we combine the two volume terms. The reason why I have a negative sign here is that because you have a negative sign from here, so it just get this in. And basically what you see is that this is the strain energy per volume, right? So basically what you see is that if you look at this equation, okay, and if you want, you can actually combine these two terms all together. We call this delta G effective. Okay, so you see that the overall free energy difference still can be written as a volume term and a surface term, right? And the volume term has actually two different sources. One is the bulk free energy reduction, it's a driving force, but then this driving force is reduced or diminished or damaged a little bit by the strain energy increase of the system. Okay, so you altogether can call this a delta G effective. Okay, so it's just a reduced driving force. Okay, so the condition that you can still have a nucleus form is that the bulk free energy reduction has to be much larger than the strain energy increase. Otherwise, you wouldn't have any driving force in the system. Okay, but anyway, so mathematically, you can see that the after we combine these two bulk terms together, it has a very nice mathematical form. Okay, so the next things, the next few steps will be very straightforward. Clearly we can still analyze the free energy curve as a function of radius r, right? So in here I listed all three terms in the overall free energy change. You have clearly this surface term, right? And you also have a very slow. Let me show this, which I think is useful. So you're gonna have this is positive volume term as well. Okay, this may not up to the scale, but this term is basically proportional to the string energy contribution. Okay, for small r, the interface contribution going to be more significant, but this is going to be overwhelmed for large R. Okay, but anyway, this is bad drawing, but you get the idea. Okay, and this is my delta GV, which is the bulk free energy reduction. Okay, so what I'm showing here is that you basically combine this volume term with this volume term. Okay, so overall, you still get a driving force, but this driving force is reduced a little bit by this delta GS. Okay, so that's basically what you see. But even if now basically, you can forget about this delta RG, right? But if you look at this bulk term and this surface term, if you combine them together, okay, you're still gonna get the curve like that, right? Okay, but as you can probably imagine, the consequence of have a reduced driving force is that the R gonna move to the right, R star gonna move to the right. So this is exactly what you see, right? So because in this case, we still have the spherical nucleus, so the nucleus is going to grow in size. Now, this is our condition for the critical nucleus size, right? And we just take derivative of this delta G with respect to R. We set that to 0. We can easily find what is the critical nucleus size, which is this one. Okay, again, these two terms are the overall driving force. We can call this delta EG. If we call that, you see this has the exact same mathematical expression as we obtained for the solid liquid transformation or liquid solid transformation. And for the energy barrier, okay, which is defined in the same way, we're just plugging R star back into this equation and we naturally get this expression. Okay, so basically you see from both mathematical analysis and our physical intuition, the only difference between the solid and the liquid in case of homogeneous nucleation is that you have the bulk free energy as driving force reduced a little bit or reduced a lot, depending on what is the bulk string energy in the system. Okay, so that's one distinction. Okay, so there's other distinctions, okay, which I do not have a slide for you here. Okay, the thing is that, hello, I think you got a question. Okay, so the thing is that, in the solid liquid transformation, okay, so it's very reasonable to assume that you have a homogeneous, kind of a spherical nucleus, right? But in the case of solid transformation, in most cases or more frequently, you will see that you're going to get a very non-spherical nucleus, a kind of a polyhedral nucleus, compatible with the symmetry and surface energy and the original crystal structure of your alpha phase. Okay, so that is also one thing which is quite different from this one. And if you do have something like that, okay, a polyhedral nucleus, and one important distinction between this is that each surface is going to have a different surface energy because each of this beta alpha interface is going to have a different orientation with respect to the original alpha phase field. And for different orientations, you have different grain boundaries and you can have different energy. Okay, so you cannot simply write something down like that. You have to take care each of the interface separately. Okay, this complicated the calculation a little bit, but it wouldn't change the idea. Okay, so for that reason, I wouldn't be able to talk about those things. If you're interested in those or your research is related to that, there's very nice discussion of this topic in the textbook. So I'll just skip that. But I do want to point out, okay, another quite different aspect of solid-solid nucleation is this anisotropy of the interface. Okay, so with that, I think this is all I want to say about the homogeneous nucleation. And we talk about the driving force, we talk about the barrier, and then we can, basically follow the exact same procedure. We can work out the nucleation rate. Okay, so this is first we write down the nucleus concentration, which is proportional to the Boltzmann factor. Inside this one, we have the energy barrier. Okay, so uh, and then the nucleation rate is basic homogeneous nucleation rate is basically the product of the nucleus concentration, what you already have, and times the I think F is a rate of atom added to a existing nucleus per unit time. Okay, and this can be written as omega times another Boltzmann factor, and omega is just the vibration frequency for the atom, and this exponential Boltzmann factor is characterized by a barrier to adding atom to the existing nucleus. But anyway, this is the same that we had before. So if you combine all these terms, you have two exponential terms here. And you can, based on this, we know that this homogeneous nucleation rate is very sensitive to temperature. Okay, so again, this is very similar analysis. It only amounts to the change of delta G star. So I won't spend too much time on this one. Okay, so now I do want to say a few words about the driving force for the nucleation processes. Okay, so in the previous case, we show the driving force is proportional to delta T. Okay, now in this case, and because we'll use this later in our analysis for the growth, so I want to point out that the driving force, which is bulk free energy reduction, which is delta GV, is also proportional to delta X. Okay, so the reason for this is, I think it's probably easier to see this on the graph. So again, the reason, basically the idea is the following, right? So we have X naught as our initial composition, which is right here, okay? This is my X naught, okay? This is my initial composition. And we know that this composition is the equilibrium composition for this particular, point where the um, transformation just to start. Okay, we call this the equilibrium temperature. Okay, so now what we do is that we reduce the temperature by delta T to induce a supercooling, right? Now in this case, okay, what the system does is that at this particular temperature, the equilibrium composition of the solid and the liquid, I'm sorry, the alpha and beta phases going to be respectively XE and X beta, but XE is simply X alpha, okay? And because we just have a fairly small supercooling in our analysis, there are several assumptions we can make. The first one is that we can approximately consider this line as just a straight line, okay, over a certain distance, okay, a straight line, right? So now, if that's the case, okay, you can clearly see that if I further lower the temperature a little bit, I'm going to change my this E XE. My delta X is simply X naught minus XE, right? So my delta X is the difference between the current composition and the actual equilibrium composition of my alpha phase. Okay, so this is my delta X, which is found here. And if we're at small supercooling, if we can approximate this solidus as a straight line, we can clearly see that my delta X is linear proportional to delta T. Okay, so that is basically a very important relation. And we know that delta GV is proportional to delta T. And because delta T is linear proportional to delta X, so that's basically give us this delta GV is proportional to delta X. And what is delta X is the difference between X naught, which is the overall composition of the system, and XE, which is the equilibrium composition associated with imposed supercooling. So that's basically um, um, this. And if you look at delta GV, basically what is delta GV is this guy, right? So this is your alpha free energy curve. But if you do a double tangent construction for at this particular temperature, okay, this is a single alpha phase. This is alpha plus beta. So this difference is going to be the driving force, which is a bulk free energy reduction. Okay, so again, we will revisit this picture when we talk about the growth. But for now, I just want to point out we have this proportionality. Typically we work with delta V as delta GV as a function of delta T naught. But in here, we work with delta GV as a function of delta X. Okay, which will be more convenient for our analysis. Okay, so that's that. Okay, so I think that's pretty much all I want to say for homogeneous nucleation. Okay, yeah, I think that's just point out what is delta G. Uh, so let me see. Yeah, we still have like 10 minutes, so I think I can start the topic of heterogeneous nucleation. Okay, so as we see in the picture, let me show you. Okay, I don't have that, but if you still remember, okay, we look at a schematic plot for the nucleation for these system, right? So if you look at the if you still look at that picture, there are many different heterogeneous type of nucleations. Okay, but I think one clear message from that schematic plot is the green boundary nucleation is probably the dominant mechanism for all heterogeneous nucleation. It's most commonly seen, right? So the reason why for that is because the green boundary is particularly in these alpha grains are the places where you have the most concentration of higher concentration of defects, right? You have a lot of extra room in there. You have vacancies. You have you know stacking faults, at the green boundaries, right? You also have dislocations, you have other defects, but the green boundary is the place where packing structure or, structure-wise is most disordered. So you see that if you form a nucleus there, the chances to, use the extra room to accommodate some of the volume change will be much higher than you do this, near a dislocation. For dislocation, you can also do this, but it wouldn't have a lot of freedom for you to really adapt the volume, right? Or use that defects to reduce the contribution of the increase of volume to the total energy of the system. So I think that provides a rationale why green boundary is more favorable for heterogeneous nucleation. Okay. Now, due to these considerations, although we can apply exactly what we did here for the green boundary nucleation to other defects, but for now, we will focus on the green boundary nucleation. Okay, and we'll focus on the nucleation for these just a binary boundary, not a triple point, because binary boundary is also again a more commonly seen cases, because the triple point, if you count those things, are much smaller than these binary green boundary areas, right? So that make this binary green boundary heterogeneous nucleation the most commonly seen scenario for the nucleation, for the heterogeneous nucleation in this system. Okay, so yeah, so again, the key thing that we need to do is to write down the free energy difference so we can understand the driving force and the barrier. Okay, so again, I'm now just using our knowledge for homogeneous nucleation, because we know that, for the homogeneous nucleation, I already have these two terms. I have the surface term, I have the bulk term, which has two sources. One is increase. Okay. Now, in general, okay, because we nucleate, we form the beta phase at a defect, okay, and this defect will bring down the free energy change, or this defects will, in certain sense, we're gonna, favor the lower certain of the energy, right, associated with the defects. For example, you have a green boundary, which are a lot of stacking faults, and if you put a beta phase there, the beta phase can have binding with some of the alpha atoms which previously has no neighbors, and this will reduce the overall energy a little bit, right? And also, you can consider this delta GD is basically a favorable energy reduction, due to defects. Another scenario for this is that, as we said, if on the green boundary have a lot of extra room, so we'll insert a new beta phase in that area. You won't cause as much as strain as if you were doing this in the bulk of the alpha. So you can consider this negative contribution to the change is to bring down the strain energy a little bit, right? So, but in general, we just consider there's a defect associated, a reduction of the energy if we make nucleus there near the defects. Okay, so that's the actual term. Okay, again, this is a general consideration. We need to make this concrete. So we just work with, again, a nucleus which derived from a spherical cape. Okay, this is additional energy reduction due to interaction with defects. Okay, so uh, so now what we're going to do is, we want to do some mathematical analysis for the system, right? So what we do is we consider a particular shape for this nucleus. Sometimes we call this an embryo. Okay, so this shape is very similar to the shape that we already analyzed in our homework. For homogeneous nucleation, right? I'm sorry, for the heterogeneous nucleation in the solid liquid interface, as solid liquid the wall, right? We approximate the nucleus as a spherical cape. Okay, so basically what you see of this embryo, again, I'm trying my best to draw. So is, in here, okay, we just have two of those capes, right? You can consider if you cut this through the symmetry line, you have a cape on top and cape on the bottom. We just have two of these capes, we just glue them together through their bottom faces, which is a circle. Okay, well, basically you consider you have a spherical cape, you take a mirror image across the grain boundary, and you have another part, you glue them together, and this is what we call embryo. Okay, so why you have this? Well, because you can grow on both sides, right? Here I have alpha phase, and here I have alpha phase, so you nucleate and grow on both sides. So this is a very reasonable assumption. Okay, and if we accept that, I will not repeat all the mathematics that we did show for the heterogeneous nucleation for liquid solid transformation, but I just want to point out that you have very similar considerations here. For example, you consider the balance of the surface tension, right? Now I have to deal with three interfaces, right? Between two type of solid faces. I have alpha grain boundary. This is originally I have alpha and alpha, right, or alpha prime, whatever you want to call them. But I have a grain boundary energy. This is gamma alpha, and I have the solid the two the energy between the two interface energy between the two solid faces, alpha and beta, gamma alpha and beta, right? And at this point, everything's balanced. So I have gamma alpha beta pulling in this direction, pulling in this direction. Okay, and this alpha and alpha pulling outside. So they have to balance one another along the horizontal direction. And if we call this angle theta, basically what we have is the equation going to be 2, right, times gamma alpha beta, okay, times theta, which is the component of gamma alpha beta on the horizontal direction, equals to gamma alpha alpha. Right? This is very straightforward, and this directly gives you this expression. Okay, you can write down the angle theta as a function of the ratio between the free energy, the interfacial energy terms. Okay, so again, this is very similar to what we did for the liquid-liquid transformation. We first get the geometry relation considering the balance of the interfacial energy. Okay, and then this is not really a spherical, but we assume that we have part of a spherical nucleus. And in this particular case, we can actually write down the um, overall free energy change associated with this nucleus. Okay, so I think I will probably need to stop here. Okay, so we're used to the time, so I'll stop here. Okay, we're ahead of schedule, so I'm not in a hurry to rush this topic. I'll stop here and start recording. And in the next lecture, we're going to pick up and continue our discussion on the heterogeneous nucleation for solid-solid phase transformation and talk about the different modes for the growth of these embryo. Okay, because these things are most commonly seen in the system. So for the growth, we'll just focus on this particular example. But again, we'll get a lot of useful insights by looking at this simple example. Okay, so I'll stop recording.